People implementing RAG usually jump straight into vector search, but vector search has a lot of downsides. So first of all, it's not robust out of domain. Different types of queries need different embedding models with different vector indices. And some query types might not work at all. It's also very costly in terms of compute and storage. We have to keep our indexes in memory so we can achieve a low enough latency for search. And what we are talking about today works for everything. It works out of domain and is one of the most efficient types of search out there. You probably guessed it already. We are talking about the OG ranking function of search, BM25. Today we are continuing our series on search, on how AI is built, with David Tippett. David Tippett is search engineer at GitHub after working at OpenSearch for a long time. We talk about BM25, how it works, what makes it great, and how you can tailor it to your use case. And also how BM25 is used at GitHub's for 100 billion plus documents.
I have not used Vespa, but I can say from the people that I know that use Vespa, it's amazing. It's really good, but at the same time, it's not, I would say it's like a top 5% search engine. If you are like in the top 5% of like search users, or in the top 5% of, what is that called? Vector search users, that's where you're really picking up Vespa and you know what you're doing. Maybe not a lot of people know yet or haven't found out yet that, yeah, Vespa came out of Yahoo. It was actually went into Yahoo first in the like early 2000s and then left Yahoo. So yeah, they have a lot of lingering stuff because apparently Yahoo was a big Java shop. I don't know.
It's too much business is still being done in Java. I learned programming in Java and I still look back with dread and hatred of the courses I took.
I'm in the same boat. I'm using Ruby now, and Ruby is like one of those like mythical languages because it does so much in the background for you versus Java where you're declaring everything. You've got interfaces for everything. It is so verbose. It's painful.
That's maybe an interesting starting point. When you would have to put search engines into the same buckets as programming language. So basically, Python, the really simple one, like C, really down, Rust, like the newcomer, the really hyped one, Go, more of the cloud native one. Where would you place the different search engines?
Oh, this is perfect. Okay, I love this question because I have really strong opinions. So Weaviate is where I feel like a lot of people get started, right? It's the straightforward, super documented, painfully well documented, almost to the point where anyone could get into Weaviate and start doing something, which is great. And they're integrated to everything, LangChain, all of those things. Once you get to a certain point, though, where you're doing some more advanced relevance features, you're going to start feeling the pain there where Weaviate's just not quite scratching the itch. And that's where I feel like most people will move into one of the REST-based search engines. That's going to be like Solr, that's going to be OpenSearch, it's going to be Elasticsearch. If there was like a spectrum there in that middle ground of like search engines, I feel like Elasticsearch is the easiest to get going with. Then OpenSearch kind of sits in that middle category where it's nice because it's really flexible, but at the same time, it's also challenging because the documentation is still like coming up to speed, and OpenSearch will let you build search however you want. And sometimes that's a good thing because you can do really cool things. And sometimes that's a bad thing because you could accidentally do something where you're like, that makes no sense whatsoever. Solr, I can't really place. I don't have enough experience with Solr to say like where in that middle ground it falls. And then at the very top end, I feel like you've got Vespa. And I say Vespa is like the top end because Vespa is where I feel like PhDs go to build massively scalable, distributed like vector search applications. Vespa is always on top of the most recent research, which means they have the most cutting edge features. It's really good. But then operationally, it's challenging because it was built to be run inside of Yahoo in their infrastructure frameworks and paradigms. So running Vespa itself is not as straightforward.
Would you actually say it's like partly where the different search engines came from? So from which companies? Because Yahoo, likely they have a large infrastructure team, so they don't
Yeah.
really care about like how complex it is. What are like the different backgrounds of the different search engines you work with?
That's so funny. I'm writing an article right now, and I've said that for the last 3 podcast episodes I've recorded for myself and here, but I'm writing this really nice detailed blog post about how these engines are being built. So, like, one of the really interesting things that not a lot of people think about is how companies make money affects how they build their product. So, for like a great example is Elasticsearch. Elasticsearch, their biggest thing is their licensing. So they make it extremely easy to onboard, right? Lots of really great documentation, lots of integrations with libraries. Kibana has a lot of workflows to walk you through. And that's to get you onto the platform. And then it's lacking some of the feature richness. But once you're on the platform, the idea is you're there to stay. Versus OpenSearch, which OpenSearch is, I'm going to say, being built heavily by AWS. We'll say they're one of the largest contributors to OpenSearch. And that affects how OpenSearch is being built because AWS is like more of an infrastructure as a service type framework. And as a result, OpenSearch is reflecting that. You can pick all of the various components you want in OpenSearch. But as a result of that, sometimes it can be hard building a complete solution because you're like, I don't know which vector search engine I want under the hood of OpenSearch. I just want vector search. I don't know which vector search I want. I don't know like why I would pick one versus the other. And that makes it a little bit more challenging to get going with OpenSearch.
It seems a little bit like ship the org structure of
Yeah.
Amazon again.
Yeah.
That they want the optionality to do everything.
Yeah. And to some degree, I think it's great. I will say there are definitely advantages to being able to pick different components and how you want them to operate. But yeah, it is very painful if you don't have experience with that. And that's where I like to recommend like Elasticsearch for people like just getting started, because it's going to give you a very nice, hey, look, this is how you do vector search in Elasticsearch. And it's great, it's straightforward, and it works. But at some point, you're going to be like, hey, I want to do vectors that are more than 2,000 tokens. You're going to start running into the like bottlenecks of Lucine's vector search there.
Yeah, and if you would have to give people like a curriculum of things they should learn for search, what are like the algorithms, data structures, techniques they should learn?
No, that's a really good point. And a lot of people, they like to use search, but they don't think very much about how search is being used under the hood. So that's where understanding some of the core principles of your search engine is really important. BM25 is probably the top one that I feel like I harp on a lot. I did a RAG demo for a long time, which for those who don't know, it's Retrieval Augmented Generation, and it's big in the vector search space. But I did it with BM25 search, and people were just like shocked. They're like, that works? And yes, it does. But yeah, BM25 reverse indexes. Reverse indexes are the core component of these search indexes, and that's why they're fast for text search. And also why they're terrible at other sorts of things like joins. People are like, why can't OpenSearch do joins? And it pretty much boils down to reverse indexes and joins just don't go very well together. It takes a lot of memory to do things like that.
Can you maybe go a little bit into what is a BM25 and what makes it great?
Yeah. So this is a really interesting one because when I was getting into search, I had no experience or background. So I had no idea what any of this was. People were throwing around these terms like TF-IDF and BM25 and I was NDCG. There's a lot of terms here. And the funny thing is they're actually not that challenging to understand once you understand where they come from. BM25 is the core retrieval and scoring function for most text-based search engines. So that's Solr, that's Elasticsearch, that's OpenSearch. Weaviate and Vespa tend more towards vectors. I know Vespa has a very good index solution as well. But what BM25 is, it stands for Best Match 25. And it is, we'll say, a scoring function to say, how well does this query match this document? And it came from what was TF-IDF before, which stands for term frequency, which is like a count of how many terms, and then inverse document frequency, which I'll talk about a little bit more in just a minute. But it fixed some of the problems that they had with TF-IDF, because TF-IDF did really well at scoring documents against queries, but it had some pitfalls, like for really long documents, right? It was weighting those exactly the same as a really short document. And you wouldn't exactly weight that the same. If you had a document that had 10,000 words and one word match your query, you had a document that had 5 words and one word match your query, which is a better match? It's probably the one with 5, because out of 5 words, they chose one of the matching query words in their title. It has BM25 has a couple different parts. So maybe should I just walk through this? Do you feel like?
The key innovation from TF-IDF to BM25 is to penalize the results in the score itself and to basically have some form of regularization based on different factors. And I think this would be the most interesting way to start. How does BM25 penalize documents?
Yeah, I think that's a really good point, because one of the things they found with TF-IDF, we'll start with the first one, term frequency. Term frequency is basically the count of, again, how many terms in your query match terms in a document. Say I write the quick brown fox or whatever, and I'm searching my documents. If I have a document that is just the word, that's going to match really highly, because the matches the, and it matches it a lot of times. But you and I know that, hey, a document filled with just those, that's not really a match. That doesn't really tell us anything. There's the idea called term saturation, where, words that are repeated too much, they count, and they count a little bit less each time it matches. So there's this nice curve where it tapers off, and it says, hey, even if you include this word like 1,000 more times, it's not going to add that much to the overall score.
And this is basically within a document, right?
Yeah, within the document. Yeah. So like I'll have the word the in my query, and if the document is just all the word the 1,000 times, it's not actually going to score that much higher for each individual instance of the, which is important because we have a lot of these words in, especially the English language. I can speak heavily to that one because I know that one well. But we have these stop words like the, a, and they just don't tell us that much about, does this query match this document? So on the flip side of that, words that are very unique, anti-disestablishmentarianism, that is not going to appear in almost any of the documents, and that will score very highly because of the last part of TF-IDF, which is the inverse document frequency. And inverse document frequency is magic, I'll say, because what it does is it looks at all of the other documents in the index and it says, hey, how many other documents in this index does this word exist in? And if this word exists in one document and you have it in your query out of 1,000 other documents, that is going to contribute super highly to your score, because they're like, this is the only document that has this word, and this word is in your query. Therefore, it's very important. So that's the IDF portion of it. And again, I said BM25 is a iteration of term frequency, inverse documents frequency. So the two things that BM25 adds is the term saturation, so that repeated terms don't count more for each instance of that term. And then the other thing is they normalize for document length. And this is like a really big one. And actually, there's some new iterations of BM25, which we'll probably talk about a bit, that also help with this. But what they found was that titles tend to match really great, and then really long documents match really, really poorly. If you have two documents in the same index and one has only a few words and one has 1,000 words, those should be weighted differently, right? Because a match in one with 5 words should be like, oh, 1 out of 5 words matches versus 1 out of 1,000. So that's the second part of BM25 that changed significantly, was the ability to normalize for document length. And I'll say it's interesting because in my own day-to-day life, I don't think I appreciate this or recognize it as much as I probably should. And part of that is because we naturally break documents up into their individual components. And at least I can say within GitHub, documents in similar types of fields tend to be around the same length. Most titles aren't 10,000 words. Most titles are between maybe 10 to 20 words. Again, in that document length normalization doesn't really hit us super much. But where you would see this a lot is in things like research journals. It's like research journal search, book search. Those are the type of places where you could have a really short book, really long book. You could have a really dense paper, academic paper. You could have a really sparse academic paper. And yeah, that's where you're going to see that document length coming into play a lot.
And just to recap a little bit, basically, we have the term frequency, which basically just counts how often a term is occurring in a certain document. Then you have the inverse document frequency, which is rather answering the question like, how valuable is a term, by determining how easy is it to separate different documents or separate the different documents in your corpus from each other through the different terms. And the easier is it to separate one document from all the others, the more valuable a term is. And then you have the additional, more of a penalty factors. And in BM25, because you have the document length and you divide it by the average document length, but you also have the B factor, which is basically a hyperparameter. What can you tell me about that? How does that actually impact the results? And is there actually value in tuning that parameter?
Gosh, that is a really great question. I'll answer that with a little bit of a statement more than I don't have a lot of experience tuning the B, but what I will say is most times people do not collect the sort of data that they need to determine whether tuning that would be valuable or not. And I think that's one of the really big things. There are a handful of constants in BM25 that for a lot of people, they're good enough. But for some people in like very specialized use cases, and I'll say again, like coming back to that, different places where you might have lots of term saturation or where you might have lots of varying document lengths, where you might tune those. And I think this is actually comes back to what I think is the core problem with search in all of these search engines. I'm going to say they do a very poor job of helping people understand how to make their search better. Earlier, you talked about the explain and endpoint. And for those who don't know, the explain endpoint in Elasticsearch, OpenSearch basically gives you a breakdown of how your document was scored. And we've been talking about documents here. Documents in OpenSearch and Elasticsearch are actually individual fields and then the sum of those fields for a query, we'll say.
So basically, to interject here, is you typically don't only look at like the content of an academic paper when you're running retrieval on it, but you have multiple fields. You have, for example, the authors, you have the title, you have the abstract, and then you have the entire content. Or you might even split it up further. You split it up into introduction, methodology section. That's a hard word for me.
Yeah.
And you can basically create a scoring function over the different fields and weight different fields in a different way. And when you look at explain, it basically breaks down how much impact each field has and why it scores so highly.
Exactly. And I think this is where we need like better tooling across the board to put that in a more understandable way, though, for people just getting into the field. Because for me, I've been explaining BM25 to people for a long time, so it feels a little natural. I'm like, oh, this document didn't match because this document's much longer and it just got tanked in the ratings. But for people just coming into search, that can be really challenging because, oh, I don't understand, like that document got weighted more, but why? So there needs to be some better tooling around that.
I just want to a little bit understand your intuition behind like the two big parameters, which is like
Yeah.
the K1 and the B. It's
Yeah.
like, in which scenario would you actually increase or decrease them? So when you're looking at the saturation of term frequency, when
Yeah.
you have like high amount of terms
Yeah.
repeated in each document, would you
Yeah.
go with a higher saturation or a lower? Vice
It de-
versa.
it depends. So this comes down to what actually this comes all the way back to what do your users
Yeah.
expect. A lot of times, especially in maybe we'll say within an academic domain, there might be very like common terms across that domain. And each additional, what is that called? Each additional term might add more value. So in that case, you would want the term saturation to affect score much more. I don't remember off the top. I guess in that point, you would decrease K, if I remember off the top of my head. It's been a little bit. But so that's where you would look at that and say, hey, what do my users expect? Are they expecting repeated terms to count more? Do they think repeated terms are very important? And then on the other one, the document length. Does document length matter? Maybe you look at your documents in your index and you say, hey, look, our documents are between 10 and 25 pages. Document length doesn't matter that much. So you could decrease the impact there. Or it might matter a lot, in which case you could increase that impact on your scoring. But again, you also need to have data that says the documents that I expect are not matching. And before I would tune BM25, I would probably tune my query weights first. Because what I think most people will find is they might be weighting fields poorly. Actually, this might be a good place to talk about, like, we've talked about scoring here, and we've said scoring is per field. So a title field of a document might have one set of scores. A body field of a document might have a different set of scores. When you combine those scores, you get the total score for that document, whether that's a paper, whether that's like a record. One of the challenges is, though, the range of scores for each of these fields is going to be different. And the reason for that is fields with fewer words are going to have, let's see, much higher IDF versus fields that are longer are going to have much lower IDFs. I'm trying to make sure I'm saying that in the correct order. But the potential score of a title field might be an entirely separate range. Like it could be like, I'm going to throw out bad numbers here, like 20 to 25 could be your title field score range. And then your body field might be like 0 to 5. So this is where it gets really important to start having relevancy practice, which is where you recognize, hey, the body field regularly scores in a very different range than the title field. Maybe we should increase the boost for the body field and put it in a similar scoring range as the title field. Or maybe the body matching doesn't actually matter that much, which is what a lot of people find. Matches on title type fields tend to be really important because like you only have so many words in a title and people tend to put the most important words there. That's where it gets really important to know, what are your users expecting and are they finding what they expect to find?
Yeah, and this already goes to like how much meaning do the matches or the BM25 scores carry? Because it tends to be that on title fields, a very good match carries way more significance and relevance than if I have a very good match on a body field.
Yeah.
And this already leads us a little bit into like the BM25F, which is basically just saying like it's field based and we have a document with multiple fields. Yeah, you were already.
No, I think that's a nice segue. And actually, I'm going to be a little bit embarrassed here because I have very little experience with BM25F. But what I can say, and like OpenSearch also didn't have support for BM25F when I was there, and they still don't. It's like on the roadmap, which is a little bit of a hot take. It's been pushed back quite a few times because actually, I'm not sure why, because I think a lot of people are asking for it. But to break down why BM25F is important is we've said BM25 scores are per field. So it's either the title field or it's the body field. But what BM25F does is it calculates the scores across all of those fields. So now you get this nice combined, what is that called? Combined score, we'll say, between several different types of fields. So yeah, I think that's really interesting. I think it's interesting that OpenSearch hasn't implemented it, given how many requests I've seen for it in the community. But I think it should be coming soon, hopefully.
Yeah, and I think you can also replicate it a little bit with just
Yeah,
using BM25 on the different fields. So I think it's probably not a priority for them at the moment.
maybe. But I think it does add a lot because like it takes away some of the work that you have to do weighting all
Yeah.
those different fields to get them put into like similar ranges. And actually, we want to talk about BM25 search versus vector search. This has also been a huge problem for a lot of people because, you know, what at least OpenSearch found in most of their research is 25 does really great at, we'll say, what's called zero shot retrieval. So it's never been trained on anything. It is a very straightforward algorithm, and zero shot retrieval basically says, hey, it's never seen this example before, but it can go and find the right result. Then you have vector search, which is, it's been trained. I don't know if I would call vector search one shot, but I feel like I've probably just used that wrong, and Joe Christian's going to come light me up on Twitter. But they have very different scoring paradigms. So vector search is always between like 0 and 1. And BM25 can be a whole range of different things. Combining them, you are almost always going to get a better experience. But again, we've got scores that are in hugely different ranges. So how do you combine these sets of documents that have completely different scores? And that's where I think actually OpenSearch has done really well so far by creating like pipelining tools that allow you to do score normalization and get a single unified set of results back, which I think is cool.
Yeah. And when looking at BM25, I think like there are so many different versions nowadays.
Yeah.
If you had to pick one favorite child, what would be your favorite adaptation of BM25?
I have a hard time saying anything other than Ocampi BM25, which is like for the baseline of BM25. I feel like it's been around since 1994 was when it was like released to the world in Trek, which is what's it, Text Retrieval Conference, I think is. So yeah, 1994. That's a year before I was born for context. And it's been around all this time. And I think there's a reason for that. And I think it provides a very good generic way to score and retrieve documents. And other groups are doing things differently. I would not recommend it, but Postgres own search is, what was it based off of? I'm going to forget, of course, what Postgres search relevance is based off of. But basically, it's optimizing for how close the terms are together is one of the things that comes into Postgres retrieval function, which I think is neat. And if someone finds a way to add that to BM25, I think that is going to dramatically change how we score documents, because term proximity can add, I think, a lot of value. But
I think Postgres built it not on terms, but on top of lexemes, which introduce like a complete new area. I think the full text search in Postgres was on top of lexemes, which is more like a semantic unit of language, which I think introduced a whole lot of new issues, like what makes up an semantic unit and how that even is defined.
yeah, it's interesting. But yeah, one and this to this point, I'm not saying that you shouldn't do full text search on Postgres. But if I was doing text search on Postgres, I'd be using something like Retrieval or one of these other layers that gets added on top of Postgres. That adds back in BM25.
Yeah, I think ParadaDB is another one on top of Postgres, which adds a
Yeah.
lot of the features you have in regular search databases. Yeah, I think in the end, you should be, like you said already, you should be more oriented how your users are searching and what documents are you serving. And if you have a reason to go with a variant of BM25, which isn't the default, then you can do it. Like, for example, BM25 Plus, I think, introduces a constant to avoid like zero term frequencies,
Yeah.
especially for like very long documents. That's very valuable to have. because you
Yep.
just have a way bigger term corpus. And I think in general, you can look through the different definitions. The question is whether you will outperform like the baseline BM25 in a
Yeah.
significant way.
And that's also, it comes back to measurement. Can you measure what people want and apply that? Because that's one of the places I know a lot of people, they try a couple different things and they see which works best. But when you start to measure things, and for those who don't know, there's a lot of great ways to measure search. The best, in my opinion, is NDCG, which is like non-discounted cumulative gain. But basically, it's a measure of, hey, I searched this and I have a ranked set of results for this query. How close to the top did my highest ranked result get? And likewise the second, etc. And being able to measure that and have that measurement and then apply that to like, hey, I made a change. Are my search results getting better or are they getting worse? I think that is probably the most valuable thing you can do in a search organization, because then you can start to experiment and say, hey, can we improve query times by trying this different modification of BM25? Or can we simplify search? Do we need all of these different fields? Do we need trigrams, n-grams, etc., on and on? Or are they adding any value?
Yeah, and this, I think, like one smart thing you already said mentions like the part of search which is often underappreciated. It's not just like relevance, it's also like the other performance characteristic you might want to optimize for. Like latency is a massive one.
Oh, gosh, yeah.
Like doing a vector search on a large corpus will likely introduce some issues in terms of latency unless you're willing to take like a whole lot of like inference cost. At the same time, you might want to optimize a little bit more for like high ticket items to have like higher ticket sales. Like
Yeah.
search is very business driven, which makes it so interesting to me as like a domain because it's very oriented to more of an engineering discipline.
Yeah. I think it's a little funny though, because you highlighted that search is business driven. And I'm admittedly in a place where search isn't our core. Like in e-commerce, it is like everything, right? You tie dollars to searches. In GitHub, it's like search is valuable. Like we want people to find the right things. But the most valuable thing I think in GitHub is like, hey, are you able to develop with a community of people and interact well? So it's hard saying, hey, GitHub, we should spend a ton of money like building the most advanced search ever. And they're like, that's great. That's really cool. Does it add that much more value to people? And I will let the people decide. Comment, respond, retweet, whatever at us and let us know. Would you value a more relevant search at GitHub?
I would.
That's my own plug. This is me trying to get funding for more search at GitHub. And I will say, GitHub, you talked about latencies. This is where it gets really tricky, especially in the search domain. So at GitHub, technically all of our data is hot. We never prioritize data. Some document, some commit you created 7 years ago might be just as relevant as a commit you created yesterday. And that causes all sorts of challenges because we have 100 billion documents around that. I don't have exact counts off the top of my head, but around 100 billion documents. And we need to be able to say, hey, this is the most relevant commit for what you want. And it's really hard because you have users doing all sorts of weird things with GitHub search. We have people who are, what's the word for that? People that are basically looking for security vulnerabilities using different parameters in our search, or people that are scraping us, trying to find certain things. We have people that are just business users, like saying, hey, I'm just trying to find an issue. We have developers who are like, hey, do we have a dependency on something? And they're searching within their code base. It's a lot of different use cases, and it makes it really challenging.
Yeah. And when you're looking at a large scale search system, GitHub,
Yeah.
what do you think? How does BM25 fit into the larger search system?
Under the hood, it's technically everywhere. All of our fields, we can't afford to do, maybe I shouldn't say we can't afford to do vector search. We could probably do vector search if we wanted to, but BM25 is so incredibly cost effective. It's very hard to justify doing any other type of search other than BM25 because BM25 gives us really fast search across all of our data. And that's one actual point that might be good to bring up is There are lots of layers on top of BM25 that you use to improve search latency, that you use to improve or reduce the impact of a search in your entire cluster. So if you do an open search, you're going to hit all of GitHub, right? And that's expensive. But we can start to do things and layer things on top of that to reduce the impact of that search, whether that is filtering down to an organization. Then we can, as long as we have all of our documents routed appropriately, we can reduce the scope to just documents within that organization. Then you don't hit our entire search cluster. We reduce, I was going to say shard size, but I guess it's shards. I always confuse shards and segments in OpenSearch. It's leucine segments, and Elasticsearch and OpenSearch use shards. But shard size. So a shard size for Elasticsearch or OpenSearch should be about 20 to 50 gigabytes. And again, that way you can use the most of your CPU to search across this data. So BM25 sits as the foundation of all of that. We have all of our fields are indexed into BM25 type text fields. And then we're adding layers on top of that. Hey, we've indexed this title field 3 different ways. And the exact matches are top tier. And then maybe we'll have an ngram field, and that's like the next tier. And then the lowest would be like a trigram, if it matches on a trigram. That allows us to retrieve things that might be really hard to index otherwise, like labels that have bunches of special characters.
And I think what really nails the point home is that the different search queries you actually face at GitHub that you mentioned before, that BM25 can serve them all. And when you would be using something like vector search, you'll likely need fine-tuned models for the different types of searches you encounter. And then you need like a routing layer on top of it that basically recognizes the types of searches you're currently encountering with the user, that routes to the right type of vectors and vector model.
That's so true. And honestly, doing vector search at the scale of GitHub would be just so incredibly problematic, because for HNSW based vector search, that's all sitting in memory. And I can't even imagine what it would be like fitting 100 billion, nonetheless, a billion records in memory. And then you have some other ones. Oh gosh, I'm going to forget that. What's the other I-based vector search? I keep wanting to say IDF, but there's another more like bucketed version of vector search that allows you to bucket your vectors into different pools. And
IVF.
IVF is the one. Yep. And the challenge with that one is you're going to start losing out in relevance because, maybe you've routed it to the wrong bucket. And, so it gets really tricky. And I would like to see us using vector search, actually. I do think there is a use case, and maybe it's some sparse vectors. But we are very far away from that.
Yeah, I would actually love to know, like, how does like the storage requirements in terms of space and memory and space on disk compare between BM25 and vectors, if you have some rough estimations or some intuition on that.
Actually, this is one thing I can say that's really interesting. Vector search is wonderful because it scales, I don't want to say linearly. What am I trying to say? The size of vector documents are constant. That's where I'm getting to. So vectors, when you output them, they're of constant length. You have a 1028 token vector, and all of those individual vector tokens are going to be like a floating point 64 or something like that number. So that makes it nice because vector search, you can estimate really well what your memory requirements are. BM25, it's like throwing a dart on a board, because you start with, here's like my base document. That's great. You have your base document size, but then you might ingest it twice. What if you ingest it once with like one type of analyzer and then a second time with another type of analyzer? So I feel like BM25 becomes very challenging to guess for. One of the really funny things that I'm starting to wrestle with is our nodes at GitHub. We basically have 10x, I'm going to say 10x the amount of storage that we actually need for our BM25 vectors, because the biggest challenge we've run against is the IOPS for the storage are actually really important. Like, how fast can we execute operations against that storage? And that tends to only be available on high storage nodes. So we've got these huge nodes with like tons of IOPS, and we store, maybe we've got a node with a terabyte of storage and we're using 100 gigs on that. Now we have hundreds of these nodes, but that's all because how fast we can access the storage is actually really important to the overall latency of our search.
Yeah, nice. Can you maybe go a little bit into the technical parts of BM25? Like where the
Yeah.
index is stored, where the raw data is stored, where is all that stuff put, and how is it actually used when I index it, but also when I run some queries?
Yeah, that's a really good question. So OpenSearch and Elasticsearch, a lot of stuff is pre-computed. Like pretty much anything that they can pre-compute for a document and for an index is pre-computed. So documents as they OpenSearch or Elasticsearch, they're going to hit the REST API. From the REST API, they're going to get broken apart into all their individual terms. So all the terms get separated out, and then that's stored temporarily in a place called the translog, which is like a write-ahead log for those who are familiar with like database terms. But that's a very temporary place that it gets stored before eventually it gets like flushed to disk. And I say flushed to disk. So OpenSearch and Elasticsearch maintain a reverse index. And a reverse index is basically a hash map where there is a term, and then all of the values for that term are the documents that maintain that value. And it does this for every single term. So a document and a table or like an index in OpenSearch are very different, because a document you think of and I think of as, oh, that's the whole thing. However, when OpenSearch looks at it or Elasticsearch looks at it, they're looking at a giant table with all the terms with pointers back to the documents that contain those terms. So this layout makes it really easy to do things like IDF, because, okay, here's my term. Here's the count of how many words contain, or here's the count of how many documents contain that term. It's right there. And so we can start to store that calculation of how many terms or how many other documents contain this term. So that can be cached. Same with things like IDF. That was what I just described. So you have like all these layers of these different pieces of BM25 being cached. And that allows us to do really cool things, optimizations for only retrieving the documents that we anticipate are going to have the highest match, we'll say. And a lot of this breaks down to, it's funny, it's vector math, like matrix math, because what you do is when you have a query, you break your query into the individual terms. We're going to go retrieve those terms, those term dictionaries from the index, and then matrix math to determine which of them scores the highest. So I have, that is my, I'll say, high level or maybe low level understanding of it. I don't know that I could talk too much more specifically about it than that.
No, I think that's the misconception many people have when they go into like search databases, because most people, it looks like a document database.
Yeah.
But it isn't.
And this is also why joins get really tricky, because what you have to do to effectively do a join is you have to go and you have to calculate the scores for all of these different documents. Like if you wanted to join two, we'll say two tables, we'll say, to use like SQL terms, you have to go and retrieve all these documents. Then you have to put them into memory and you have to try and mush them together in the appropriate manners. So you miss out on a lot of the optimizations that like SQL databases can do, because they have very efficient ways of doing some of the join work ahead of time.
Yeah, it's in the end, what are you optimizing for? And
yeah.
That's, I think, something that's talked about more in like traditional database courses, that you have a workload mismatch, and that's why you actually use different databases, because the stuff you pre-compute, which is the indexes, which allows for the high performance computations that you're doing on the data, this is the stuff that actually gets you the high performance, but this also makes other computations or other workloads you could perform very inefficient.
Yeah. Yeah, and it's challenging. That's why for each of the different database types that you might pick for something, it's very important to choose like the right data model for that. A really great example is like OpenSearch is probably very similar to Cassandra in the sense that you want everything you need for that query to exist within that document. And Cassandra, I think, does that a lot. It's very different from Redis, though. Redis, you're breaking things down into, hey, I have a key and then I have a value, and I'm always doing a lookup of this key and a lookup of this value. Maybe I'll do a handful of key operations at the same time. And then versus SQL. SQL is like, hey, I want to separate each thing into their own nice little compartments. Like, these are my users, these are attributes of users that gets joined on. Maybe there's blogs, these are the blogs that belong to the users. That just doesn't make sense in something like OpenSearch or Elasticsearch.
Yeah. And what is actually something that you would love to see built in the search space?
Oh, yeah. Okay. The person who solves this challenge wins search as far as I'm concerned. So I see a lot of people, like we've talked a lot about like the newest research, what's coming out. The person who finds a way to, I'll say, automate or build a general enough system that not only does the search portion, which is like information retrieval, but also the optimization stuff. Like, hey, this was the query, this was the result. They clicked on this result though, and that was the final outcome. If someone figures out, and for this workflow, it's called learning to rank. If someone finds a way to automate, so to speak, learning to rank, or to build these relevancy tuning workflows into a search engine, that's it. They have won the search game and they will remain champion forever. And I think there are people working on it. I think actually Algolia, I've seen a lot of stuff coming out of Algolia, which is funny because they're a very proprietary search engine, but I think they are starting to do some of this stuff. Same with OpenSearch. OpenSearch actually is working on an open standard called User Behavior Insights, or UBI. And it's a standard for collecting this information so that you can automate workflows like that. To that point, I feel like OpenSearch has a head start, but the game is anyone's. If someone can figure out how to well integrate these relevancy workflows with the retrieval workflows, they're going to win.
Yeah. And what's next for you?
What's next for me?
What can you tease?
There is nothing I want more. And I'll put this out there. I'll make this public. I am working around the clock to try and get GitHub to adopt a single search result set. That is like my lifelong goal. If I can achieve that, I would be so happy, because right now I feel like the UX for GitHub, we're very much shipping the org, so to speak, with our search results. And I don't like that. I think there is a case where we build a single pane of results where you are getting the exact result you're looking for, regardless of whether you're looking for an index, regardless of whether you're looking for a repo or code, or any of these other things, which also I should say code search is very different than traditional like text search in GitHub. And I work on text search, but I would love to merge text search and code search much more closely. So yeah, the unification of GitHub search, that is like my next couple of years probably.
Nice. And if people want to follow along on your journey of trying that, and
yeah,
let's see how successful you will be, where can they do that?
Yeah, so I have a couple places that I live very frequently. I have a blog, tippybits.com, tippybits.com. I have also my podcast as well, which is called For the Sake of Search. And For the Sake of Search is probably a much more search-focused podcast where I've been talking with people about what does it look like to hire a search engineer? What does it look like? What are different companies doing in the search space? You talked about ParadeDB. Actually, they were one of my, I think they were my first ever interview on the podcast, which is cool. So yeah, there's a lot of different things I'm talking about there. And yeah, follow along and also let us know. Does GitHub search suck? How can we make it better? I'm happy to hear.
So what can you take away when we're building search systems? I think first is search is never just about relevance, but about the user experience. So you want to align with what the user expects and also what his information need is. So for example, for GitHub, they have a lot of different use cases they have support. So for example, what he mentioned was finding security vulnerabilities, exploring code bases, managing repos, finding out commits, finding out documentation, finding out issues. And each requires a different prioritization of fields, different boosting strategies, and possibly it would even require like distinct search workflows. So you actually need a technology which can handle a lot of different types of queries and different types of documents as well. And this is where BM25, in my opinion, really shines, because it is very good at this zero-shot retrieval. So without having seen like any of this query before. And at the same time, its strength is in its simplicity and efficiency. So when we are building search engines, most of the time when we are building on top of like a bespoke search database, like Elastic, OpenSearch, Vespa, we are already at a point where we actually have to go distributed. So we have a large corpus. And BM25 is really suited for these scenarios because it's so lightweight and computationally efficient, especially compared to vector search. And this makes it really unbeatable for cases like GitHub, where you have an immense scale, cases where you have a lot of different types of queries, but you can't easily differentiate between them, or you don't have the time or the latency to differentiate between them. So if you would have the case where you really can classify easily, hey, it's a certain type of search where the user cares more about the accuracy, then you can pipe to a slower type of query or pipe to a vector database and run the search there. Then you could basically have a vector database plus a regular search database and basically decide on query time where to go. But this also isn't possible in the GitHub sake because you never know what the user or what types of document the user is searching for. And they have like such a large corpus, which would be interesting where to place them basically and how much memory the HNSW index would take. For the future, I think what becomes more and more interesting is standards like the user behavior insights. I think it came out of OpenSearch, which is trying to standardize how to integrate user behavior, like click data, dwell time, into retrieval systems and also into retrieval algorithms. I think this might make it easier to build learning to rank algorithms and for a lot of people, because you suddenly have a unified data structure, which is the main thing I think that UBI put forward, a data structure basically for the user behavior and how to store it, which should make it easier to basically train the algorithms like learning to rank and use them in your search system. I think you should always, like in the end for me, search systems, it always comes down to the architecture and to how well you actually scope the problem and understand the problem you're trying to solve. Because in search systems, you really need to figure out in advance what you're optimizing for. Whether it's really low latency, whether it's high accuracy, high recall, whatever, or whether it's like really low cost when you have a really large scale system, like in GitHub's case. These types of architectural decisions have to be made like mostly upfront because it's really hard to change it once you already have all of your data in a search database and it's already indexed and set up. Otherwise, thanks for joining. We will continue with more on RAG soon. So subscribe. Also leave a review, especially on Spotify and Apple. And if you have any questions, any wishes on different parts of search you would like me to go into or get a guest on, I should have on the podcast an interview, feel free to shoot me a message. Otherwise, I will talk to you next week.